Okay, I'm starting.
Live now.
Okay. Hello, everyone. My name is Ismail. I'm a PhD student in Software Research Group in ETH Zürich. Today, I'm going to discuss processing using memory in real DRAM chips. And I'm going to discuss two papers. First paper published in HPC 2024 called Functionally Complete Boolean Logic in Real DRAM Chips. And the other one is published in DSN 2024. It's called Simultaneous Many-Row Activation in Real DRAM Chips. So let's start with the first one. Our motivation in this work is that processing using DRAM can alleviate the performance and energy bottlenecks caused by the frequent data movement between main memory and processing elements such as CPU. And prior work showed that existing off-the-shelf DRAM chips can perform 3-input measured and 2-input and an OR operation without any modification to DRAM. But the problem is that these proof of concept demonstrations on off-the-shelf DRAM chips do not provide functionally complete operations such as NAND or NOR, NOT operation, and more than 2-input AND and OR operations. In this study, we test a total of 256 DDR4 chips from two major manufacturers, and we observed that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR and NOR operations with very high reliability. Data pattern and temperature only slightly affect the reliability of these operations, less than a 2% decrease. So here's the outline of my talk. I'll start with a brief background on DRAM. So here we have a DRAM model. It consists of multiple DRAM chips. Inside the DRAM chip, we have multiple DRAM banks that are connected through chip I/O. And inside the bank, we have multiple subarrays and sense amplifiers. Now, when we take a close look into subarray and sense amplifiers region, we see that subarray is organized as two-dimensional array of DRAM cells and a row of DRAM cells called DRAM row, and they're connected through word line. And the column of cells are connected to sense amplifiers through bit lines. In the modern DRAM chips, we have architecture called DRAM open bitline architecture. Here, the important part is that two subarrays share a common source, just called sense amplifier there. And they're connected through the bit lines. In the upper subarray, we have bit line. In the lower subarray, we have bit line bar. So the caveat here is that when you activate a row, for example, in the upper subarray, in the lower subarray, it's not activated, and their bit line serves as the reference for the sense amplifier. And the sense amplifiers consist of back-to-back NOT gates. That means that after a successful activation operation, when bit line has a value of A, the bit line bar will have the negated value of A. So let's see the major DRAM operations related to this work. First one is activate, which fetches the row's content into sense amplifiers. Second one is the column access, basically read and write the target column and drive the value to the I/O. And the precharge, which prepared the subarray or specifically bank for a new activation command. Let's take a look at our goal and overview in this paper. Our goal is to understand the capability of off-the-shelf DRAM chips beyond just storing data and rigorously characterize the reliability of this capability. To this end, we demonstrate that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in two neighboring subarrays, can perform NOT operation with up to 32 output operands, and can perform up to 16 input AND, NAND, OR and NOR operations. Now let's look at our experimental methodology, experimental infrastructure to test DRAM chips. We use an infrastructure developed from DRAM Bender. This infrastructure enables us to have a fine-grained control over DRAM commands, timings, and temperature. And this study, we test a total of 256 DDR4 chips from two major manufacturers. and we cover different die revisions and chip densities. As a side note, we also test other major manufacturer Micron as well. However, we couldn't observe a successful bitwise operations on those chips. You can take a look at our paper to gain more insights, but the basic hypothesis was when we violate the timings to perform these operations, those chips somehow ignore that the while to be activated rows comment so that we cannot activate multiple rows. As a result, we cannot perform bitwise operations. Now, in our testing methodology, we focus on neighboring subarrays, which share a common key component called shared sense amplifiers. And our command sequence is the same throughout the study, which is activate row A, precharge, activate row B, where row A is in subarray X and row B is in subarray Y. We sweep the row addresses and row addresses, which is row A and row B, to cover all rows in those subarrays. And we sweep the timing parameters between activate to precharge and precharge to activate. And now let's look at our first characterization results, multiple row activation in neighboring subarrays. So our key observation is that activating two rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So again, we have subarray X and subarray Y here. Now, in the, let's say, specification, we have this timing parameters. You issue activate row A, you wait 36 nanoseconds, which is called TREX, and then you issue precharge, which will precharge the rows. And then you wait for 14 nanoseconds or 13 to 15, which is TRP. And then you issue activate row B. In this sequence, you activate only a single row at a time. However, when we violate these timing parameters, we observe that we can activate multiple rows in two neighboring subarrays. So to understand which and how many rows are simultaneously activated, we sweep row A and row B addresses. Now take a look at our key results. We observe that off-the-shelf DRAM chips have two distinct sets of activation patterns in neighboring subarrays when these two rows are activated with violated timing parameters, basically in quick succession. First set is that exactly the same number of rows are activated in each subarray, and we observe that we can activate up to 16 rows in each subarray, a total of 32 rows. And the second pattern is twice as many rows in one subarray are activated compared to its neighbor subarray. We observe that we can activate up to 16 rows in one subarray while activating up to 32 rows in the other subarray, which is a total of 48 DRAM rows. So key takeaway is that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in two neighboring subarrays. You can find more results and more hypotheses in the paper, how and why we can activate these rows. And in the next paper, we dive into this circuitry that enables us to activate multiple rows. So now let's move on to our first bitwise Boolean operation, NOT operation. So in this operation, we will use multiple row activation we will leverage multiple row activation. Here we have two cells, source, SRC, which we call source, DSD, which we call destination, and they're in the neighboring subarrays. Now we are focusing on only cells to understand the key idea. Here they share a common source, which is not back-to-back NOT gates. So our key idea is that to connect these rows here, cells, through a NOT gate by simultaneously activating them. Assume we issue activate the source, which will drive its value to the bit line, and the negated value indicated as purple, highlighted as purple, is in the bit line 1. If we activate destination without precharging those bit line, what we will have is the negated value of the source in the destination cell. because of because bitline bar has the negated value of the source. Now take a look at how we perform this in a lower abstraction level. Now again we have two cells, source and destination, and assume that they have they have ground in the beginning and bit lines are precharged, which are VDD over 2. Now we first issue activate source, which will connect source to the bit. And then we wait for nominal timing parameters TRAS, which will drive bitline to the ground and drive bitline bar to VDD. And then we issue back-to-back precharge and activation. What happens is that it will connect destination to its bitline and keep the sense amplifier still enabled because we violate the, let's say, prevent this happening, a precharge circuitry. And destination's bitline is still at VDD. As a result, when we wait long enough, the negated value of the source is written to destination. And our characterization methodology is similar to the previous one. First, we sweep row A and row B addresses in the neighboring subarrays to understand which rows and how much we can perform this operation in terms of reliability. And we sweep DRAM chip temperature from 50 degrees Celsius to 95 degrees Celsius. Again, as a side note, most of the DRAM chips supports up to 85 degrees Celsius. When we go above 85 degrees Celsius, it needs to be refreshed at 2x more. So basically, it's a bit out of spec, but it's not out of spec. So let's take a look at our reliability metric, which we call success rate, and we define it for a DRAM cell. Here we define success rate as a percentage of trials where the correct output of a tested operation is stored in the cell. So we perform a total of 10,000 trials and we report each DRAM cell's success rate. Here we have an example. Assume we have 4 trials and half of them fails, half of them successful. We call for this specific cell, the success rate is 50%. So our key takeaways from NOT operation is that off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows, and temperature has a small effect on the reliability of these operations. So let me show you the data. Before that, I'll introduce the axes. So first, x-axis. In the x-axis, we have the number of destination rows, the rows that the negated value is written to. And the y-axis, we have the success rate. And we use a box plot which shows the distribution of the DRAM cells that we test. And the bubbles, like white circles over there, shows the mean. And we observe that there is at least one DRAM cell that can perform the NOT operation with a 100% success rate. And we conclude that off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. And next, we evaluate the impact of temperature. For this experiment, we use destination cells that can perform NOT operation with more than 90% success rate at 50 degrees Celsius to maintain a reasonable experiment time. Because we sweep a lot of temperature values, as you can see from this figure. We use 5 different temperature levels, 50 degrees Celsius, 60, 70, 80, and 95 degrees Celsius. And we observe that the most vulnerable one, which is 32 NOT operation with 32 destinations, from 50 degrees Celsius to 95 degrees Celsius, there is only 0.2 variation in average success rate. We conclude that temperature has a small effect on the reliability of these operations. And now let's take a look at the last Boolean operation that we present in this paper, AND, NAND, or AND NOR operations. Our key idea is to manipulate the bitline voltage to express a wide variety of functions using multiple row activation neighboring suburbs. So here we have again 2 neighboring suburbs. Cell A and cell B are in the upper subarray, cell X and cell Y are in the lower subarray. And here we precharge the circuitry, precharge the DRAM, which means that we set bit lines to a fixed reference voltage, which is VDD over 2 in this case. When we perform multiple row activation, what happens is that the bit lines, before sensing, it becomes the function of the data that is stored in the activated cells. So for the upper subarray, the bit line becomes the voltage function of A and B. And the lower subarray, the bit line becomes the function of X and Y. After this charge sharing ends, sense amplifier will compare voltage in the upper bit line and lower bit line and senses towards 1 or 0, depending on the values in the cells. So that was our key idea. Now let's take a look at in an example how we perform AND and NAND operations in 2 input. So here again we have 2 neighboring subarrays. Upper subarray we call it reference subarray, and lower subarray we call compute subarray, ref and com. In the upper subarray, in the reference subarray, we store VDD and VDD half. So VDD half is possible in off-the-shelf DRAM chips due to a FRAC DRAM paper that's shown that we can store these values in real DRAM chips. So, and the compute subarray assume we have X and Y in 2 sets. So again, we issue back-to-back activate and precharge commands to activate these rows simultaneously. And what happens is that the bit line becomes the function. So to keep these things simple, we can assume that the bit line becomes the average of the, let's say, values that are stored in the activated sets. For reference subarray, it becomes the average of VDD and VDD half. For the compute subarray, the bit line becomes average of X and Y. So now we will iterate all the possible input values for X and Y, and we will see the results after every let's say multiple row activation. For sake of simplicity, assume that VDD is 1, ground is 0. The first example is that first case is that where X and Y are both 0. What happens is that when X and Y are 0, the upper bit line becomes the average of VDD and VDD half as we discussed, which means that they become 3 VDD over 4. For the compute subarray bit line, it becomes the average of X and Y. In this case, it's ground and ground. The average is ground. So sense amplifiers at the end of this charge sharing compares the voltages on these bit lines. Since 3 VDD over 4 is higher than ground, reference subarrays will have VDD, but compute subarrays will have ground. So the result for this truth table row entry is that compute subarray is 0, reference subarray cells are 1. Now the second case, where X is 0 and Y is 1. Again, the upper bit line becomes 3 VDD over 4. Now we have X as 0, Y is 1. The average of these 2 cells is VDD over 2. However, still it's lower than 3 VDD over 4. As a result, reference subarray will have 1, compute subarray will have 0. For X is 1 and Y is 0, doesn't matter. It's the same as previous one. Compute subarray becomes 0 and reference subarray becomes 1. And for the last case, where X and Y is 1. Here, what happens is that now the compute subarray's bit line is VDD, which is higher than 3 VDD over 4. As a result, compute subarray have 1, reference subarray will have 0. And as a result, as you can see the truth table, this compute subarray cells becomes the AND of X and Y. Reference subarray becomes the NAND of X and Y. As a result, we can implement this 2 input AND and NAND operations. By doing so, similarly to this 2 input and an NAND operation by carefully manipulating the reference subarray cells, we can express AND, NAND, or and NOR operations. For more details, please check our paper. You can find a lot of, let's say, hypotheses and mechanism that enables this. And also we have the examples for OR and NOR and many input AND, NAND, OR and NOR operations with some figures. So the characterization method is the same as before. We sweep rows, row addresses, and our key takeaways are off-the-shelf DRAM chips can perform 2, 4, 8, 16 input AND, NAND, OR and NOR operations. They can perform these operations with very high reliability, and data patterns slightly affect the reliability of AND, NAND, OR and NOR operations. Here in the x-axis, we have the number of input operands from 2 to 16, and the y-axis, we have the success rate. And the hue, each colored box in X text will show the operation. So our key takeaway from this plot is that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR and NOR operations. And we observe that with 16 input AND, NAND, OR and NOR operations have very high success rates. And we also evaluate the impact of data pattern on those operations. So here we see for just one operation for NOR, and data we evaluate 2 data patterns, all ones or all zeros, or random, to understand if there is any basically a bitline interference between sets. Then they have a random value instead of having all ones or all zeros. We observe that there is less than 2% variation in average success rate across all number of input operands. And this is actually consistent across all tested operations. And we conclude that data pattern slightly affects the reliability of AND, NAND, OR and NOR operations. So in the paper, you can find more details about hypotheses and key ideas to perform NOT operation and many input AND, NAND, NOR operations, as we discussed. And you can find more results on how the reliability of these bitwise operations are affected by the location of activated rows, the temperature for AND, NAND, OR and NOR, DRAM speed rate, chip density, and die division. And we discuss on the limitations that we faced when we test off-the-shelf DRAM chips. So our paper is available on arXiv and also is open sourced. You can find it on GitHub. And now let me conclude my talk for this paper. So in this paper, we experimentally demonstrate that off-the-shelf DRAM chips can perform functionally complete Boolean operations, up to 16 input AND, NAND, OR and NOR operations. And we characterize the success rate of these operations on 256 off-the-shelf DRAM chips. And we observe that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR and NOR operations with very high success rates. And data pattern and temperature only slightly affect the reliability of these operations. Our hope and belief is that these empirical results demonstrate the promising potential of using DRAM as a computation substrate. So that was this paper. Now I'll move on to the second paper. Geraldo, do we have time still?
Yes, please go ahead. And there is no question on YouTube as well.
Okay, if there's no question, okay, I'll continue. So for this paper, there are very similar contents. I'll skip them because we already discussed, but I'll go in more detail into some aspects of this paper. So as I said, this paper is published in DSN 2024, this year in June. It's called Simultaneous Mini-Row Activation in Off-the-Shelf DRAM Chips. And let's get started with the executive summary. Again, our motivation is that processing using memory or processing using DRAM elevates data movement bottlenecks. And off-the-shelf DRAM chips can perform MAJX 3 and in-DRAM copy operations. In this paper, our goal is to experiment to analyze and understand the computational capability of off-the-shelf DRAM chips beyond the prior works and the robustness of such capability under various operating conditions. To this end, we conduct an experimental study on 120 DDR4 chips from two major manufacturers, and we observed that off-the-shelf DRAM chips can perform MAJX5, MAJX7, and MAJX9 operations, and copy one DRAM row to up to 31 different rows at once. We observed that storing multiple redundant copies of majority's input operands, and we call input replication, drastically increases robustness. And operating conditions such as temperature, voltage, and data pattern affect these operations' robustness by up to some extent. And our code is available online, and it's artifact related. You can search for this. And now let's move on to our motivation and background. As you already showed throughout this course, data moment is a bottleneck in today's systems, and we need to pay a great system cost to process data. And as you already know, I believe more than 60% of total energy spent on data moment. And two main approaches for this one is processing near memory and processing using memory, as you all know. And in this paper, we focus on processing using memory to use analog operation principles of memory cells to perform computation. And we already discussed the DRAM organization, so I'm going to skip. And also DRAM operations. Now let's take a look at some, let's recall the row clone operations for this paper. So what we do is that in row clone, we copy source row content to destination row. What we do is that we activate source, it asserts the source word line and derives the bit line with the source value. As a result, it fetches source content to sense amplifiers. After that, we activate destination, and bit line is still at source voltage, and sense amplifier is still enabled. As a result, source content is copied to destination. And you already know measured of 3, but let me give you a recap. Here, we perform measured 3 by activating 3 rows simultaneously. So here, we first assert 3 rows word lines, and then these 3 rows perturb bit lines simultaneously. And sense amplifiers sample the output of the measured. Basically, here we have A, B, and B. The result of measured 3 is B. So in this paper, our goal is to understand the capability of off-the-shelf DRAM chips and experiment to analyze the robustness of such capability under various operating conditions. To this end, we use this same infrastructure, DRAM vendor, DDR3, DDR4 testing infrastructure, and enables us to have a fine-grained control over commands, timings, temperature, and voltage. And we tested a total of 120 DDR4 chips from 2 major manufacturers, SK Hynix and Micron, and we cover different derivations and chip densities. In this paper, we focus on a single subarray where we have multiple rows in that subarray, and we use the same key command sequence as we used in the previous paper. Activate row A, precharge, and activate row B. And we sweep those row addresses to understand how, let's say, multiple row activation works in the same subarray. And we also sweep the timing parameters. So we test different temperatures from 50 degrees Celsius to 90 degrees Celsius, and we test the various word line voltage levels from 2.5 volt, which is the nominal case, down to 2.1 volts. And we use a metric we can call success rate, which we refer to as the percentage of DRAM cells that produce correct output of a tested operation in all test trials. We tested a total of 10,000 trials. And here we have an example there, 3 in DRAM row copy operation, and the first bit line, let's say the first cell, leftmost cell, is produce the incorrect output in one of the trials. So we say that for success rate for this example, 66.67%. Now let's take a look at how we activate many rows in real DRAM chips. Observation is similar. We activating 2 rows in quick succession can simultaneously activate many rows in a subgroup. Again, we violate these timings to activate multiple rows at the same time. And we have a hypothesis. This is because it's possible due to the hierarchical DRAM row decoder design. So we have a DRAM subarray. What happens is that when you issue ACT, you give the row addresses. Row decoder decodes this row address and asserts the corresponding word line. And we know that, at least from prior papers and some books, that DRAM has hierarchical decoder circuitry to, let's say, assert the word lines as fast as possible. So what happens is that when we give the row address, it's, let's say, split into many parts, and DRAM feed those individual parts to different states of decoder circuitry. And at the end of the result, we assert one word line. So let's try to illustrate this row decoder circuitry as a tree. So assume that we have here the root, which is you can think of the subarray, let's say subarray enable, or the choosing the subarray as a starting point, and the leaf is the word lines. So assume that each level is the one represents one stage, and each node is the decoder output. So now let's take a look at what happens when we activate a single row as a normal DRAM operation. So we should activate row A. It first needs to decode the row address, and it asserts the corresponding signals at the same time in parallel in all stages. As you can see, there are some instances that let's say, repeated. More than one nodes are asserted in a level. For example, in the stage 4 and stage 5, there are multiple nodes that are asserted due to this hierarchical design. And we follow the asserted nodes path from root to leaf, and we assert the word line name. And then we wait long enough, and then we issue precharge, which will be assert every, let's say, corresponding signals, and as a result, they assert the word line. Now, let's see how we activate multiple rows. So back-to-back activation commands with violated timings asserts many more signals in the row decoder. So first, again, the same example, we activate row A, which will assert many signals and asserts word line A. And then we issue back-to-back precharge and activation command. What happens is that we don't give enough time to precharge circuitry to assert the word lines. And we activate another row. What happens is that as a result, row decoder will keep the previously asserted signals active and decode row B's as address and assert the corresponding signals. Assume that this is the asserted signals for row B highlighted as orange. And then it will also follow the newly asserted nodes path. And as a result, we will activate many more rows than just 2 rows in DRAM. So we observe that we can activate 2, 4, 8, 16, and 32 rows in a single subarray. So for more details and discussions about this row decoder circuitry, you can check our paper. So to understand which rows are simultaneously activated, what we do is that we issue write. So how this works? Assume that we activate row A, precharge row B, which will assert many rows in that subarray. To understand which rows are simultaneously activated, we need to understand those rows change write. So to understand that, we issue write. How write works is that in a normal operation, you activate to giving the row address as an input. But for write, you don't give the row address, you give the column address. So it's basically in DRAM when you give the when you issue the write, it's just writes the activated row in that bank. So here, it's the same. When you activate multiple rows and then you issue write, it will eventually write to the rows that are activated. So that's our, let's say, the methodology. If the rows are activated, write command overwrites all of the activated rows content. So here we carefully sweep row A and row B and timing parameters between each command in the command sequence, and we sweep temperatures and word line voltages. And our key takeaways from this experiment is that off-the-shelf DRAM chips are capable of simultaneously activating 2, 4, 8, 16, and 32 rows. And simultaneous mini-row activation is highly resilient to temperature and word line changes. So here, let me introduce our plot. Y-axis shows the percentage of cells overwritten with write command. X-axis shows the number of simultaneously activated rows. And here we have box plot, but we don't have boxes because it's almost, the distribution is almost at 100% with some exceptions. And the average for up to 16 is 99.99. And average for 32 row activation is 99.85%. That means that we can write, when we issue act per act, we override 99.85% of the cells that are activated in the activated rows. As a result, we conclude that off-the-shelf DRAM chips can simultaneously activate 2, 4, 8, 16, and 32 rows in the same subrow. And in the paper, we also evaluate the impact of temperature and voltage. We observe that increasing temperature up to 90 degrees Celsius has a small effect on the success rate, and reducing word line voltage only slightly affects the success rate of simultaneous mini-row activation. So by leveraging simultaneous mini-row activation, we observe that we can perform MAJX, where X is higher than 3. We can increase the robustness of MAJX operations, and we can copy one row's content to multiple rows. Now, let's take a look at the first one, majority of X operation. So here, we activate multiple rows at the same time to perform majority of X. Here we assume we activate 5 rows here, 2 of them has A, 3 of them has B. We can implement majority of 5, which is result as B. And if we activate 7 rows, we can implement majority of 7. However, for MAJX, we need to activate X rows simultaneously. But we can only activate 2, 4, 8, 16, and 32 rows simultaneously. The question is, how do we perform MAJX while simultaneously activating more than X rows? The answer is making some rows neutral during the MAJX operation, using the frac operation, again, introduced by prior. So here you have 5, majority 5 with 5 row activation, which is equal to a majority 5 with 8 row activation, where 3 of them is neutral. And the second one is, second use case for us is to increase the robustness of MAJX operations. So the key idea is storing multiple copies of MAJX input operands can increase the robustness of MAJX operations. So we have MAJ3 here, A, B, and B, and assume that the rightmost bit line results in incorrect, let's say, output. So what do we do to increase the robustness or the success rate is that we copy let's say, the cells to perform MAJ6, which is, and the functionality is the same as MAJ3. So the left measure 3 and right measure 6, in the functionality level those are the same. But by doing that, we amplify the bit line voltages. So the deviation when you, let's say, activate 3 rows, it's not as high as when you activate 6 rows. As a result, you can produce more correct results compared to the not, let's say, replicated input measured operations. So our characterization methodology is same as before. And key takeaways from measured X operations is that off-the-shelf DRAM chips are capable of performing MAJX5, MAJX7, and MAJX9 operations. Storing multiple copies of majority input operands significantly increases the success rate, and voltage and temperature slightly affect the success rate, whereas the data pattern affects significantly. Here we have a plot which consists of multiple operations, MAJX3, MAJX5, and MAJX7. And the y-axis we have success rate. And the x-axis shows the number of simultaneously activated rows. And the hue shows the data pattern, but for now we focus on the single one. So here we observe that off-the-shelf DRAM chips are capable of performing MAJX5, MAJX7, and MAJX9 on top of MAJX3. And when we replicate the input, for now, let's take a look at the measured tree. On average, there is 31% increase, and this is consistent across MAJX5, MAJX7, and MAJX9. And even in MAJX5 case, it's 57% increase. So as a final average success rate, MAJX3 has 99.68% success rate, whereas MAJX5 has 90.49%. And we conclude that storing multiple copies of measured input operands increases success rate drastically. And now let's take a look at the data pattern impact. Here we observe that when we use random, there is an interesting decrease. And this is also consistent across all measured operations. On average, there is 11.52% decrease on success rate, and in some cases it's up to 32.56%. And we conclude that data pattern significantly affects the success rate of MAJX operation. And in the paper, we also sweep temperature and word line voltage to see their effects, and we observe that temperature slightly affects the success rate of measured X operation, and word line also has a small effect on the success rate. And now let's take a look at our final operation that we introduced in this paper, multi-row copy. So the key idea is to simultaneously activate many rows to copy one row's content to multiple destination rows. As you may remember, in row clone, we have one source and one destination, and where we copy the source content to destination. In this case, in multi-row copy, we have again one source, but we have multiple destination rows. To be able to copy source data to multiple destination rows, we activate them simultaneously. As a result, we copy source data to destinations rows. Again, a characterization methodology is the same as previous one, and our key takeaways from this experiment, from multi-row copy experiments, is that off-the-shelf DRAM chips are capable of copying one row's data to 1, 3, 7, 15, and 31 other rows at very high success rates. And multi-row copy in off-the-shelf DRAM chips is highly resilient to changes in data pattern, temperature, and word line voltages. So here again, in the y-axis, we have the success rate again. In the x-axis, we have the number of destination rows from 1 to 31. And as a box plot, you don't see any boxes because the success rate is too high in most of the cases. We observe that up until 31, the average success rate is more than 99.98%. And as a result, off-the-shelf DRAM chips can copy one row's content up to 31 rows with a very high success rates. And we also investigate the data pattern effect, and this plot this is a line plot, shows the average success rate for each data pattern in each text, which is the number of destination rows. We observe that there's at most 0.79% decrease in the average success rate. We conclude that data pattern has a small effect on the success rate of the multi-row copy operation. We also analyze temperature and word line voltage effect, and increasing temperature up to 90% has a very small effect on the success rate, and reducing word line voltage again only slightly affects the success rate of these operations. And in the paper, you can find more details, hypotheses on the key ideas on hypothetical row decoder circuitry, input replication, and more characterization results for power consumption of simultaneous multiple row activation, effect of timing delays between activate and pre-charge and activate comments, and the effect of temperature and word line voltages, which is, let's say, in a figure. And we also conduct circuit level experiments for input replication. And we also discuss the potential performance benefits of enabling new in DRAM operations by using measured-based computation and content distraction-based cold boot attack prevention scenarios. And again, we discussed the limitation that we faced when we test off-the-shelf DRAM chips. Our paper is available on arXiv, and our work is fully open source and artifact evaluated. You can find our this paper's code base and the previous paper's code base in our GitHub repo. And let me conclude my talk for this talk. Let me conclude my talk for this paper. So the experiment demonstrated off-the-shelf DRAM chips can simultaneously activate up to 32 DRAM rows in the same subarray, can perform MAJX3, MAJX5, MAJX7, and MAJX9 operations, and can copy one row's content up to 31 DRAM. In this paper, we characterize 120 DDR4 chips, and we observe that storing multiple copies, MAJX input operand drastically increases the success rate. Voltage and temperature slightly affect the success rate of MAJX operations, whereas data pattern affects significantly. Multi-row copy is highly resilient to changes in all tested parameters. And again, we believe and hope that these empirical results demonstrate the promising potential of using DRAM as a computation substrate. And that concludes my talk for this lecture, I guess. Geraldo, do we have any questions or something?
Ismail, we still don't have any questions from YouTube. But then maybe I ask you a quick question.
Sure.
So what is next?
I don't know. I mean, so for real DRAM, you mean?
Yes, yes. Like, do you see commodity off-the-shelf chips as a viable solution for processing using DRAM computation?
No, right now, no. So I think if you want to really enable processing using DRAM, we need some modifications. As you can see, it's a very hacky way what I'm doing. There should be some official support from, it should start from the row decoder circuitry, even the interface also, but for just inside the DRAM, it should start from row decoder circuitry, and the cells are also should change because we have the process variation, right? Even if we design everything, we should we still have the process variation. So we need to do something about that. But so these papers or these lines of works show that there's a potential here. And it's good to understand what DRAM is inherently capable of, I believe.
I totally agree. That's a great answer.
Thank you.
Thank you very much for the presentation.
Thank you.
Don't have any other comments on YouTube. So I guess we can finish up for today's PNS PIM. Thanks everyone for listening. Thanks Ismail for the great talk.
Thank you very much. Okay, see you next week then.